Hello! So, some of my lovely science class have asked me for some chemistry videos because we did some revision videos on biology that were quite useful apparently. So we're looking at chemistry 2 now, and one of the main topics in that is organic chemistry, and that's the chemistry of carbon. So, a lot of it is based around oil and crude oil. So the very first thing we need to look at is, where did crude oil come from and why is it called a fossil fuel? And the first thing is, millions and millions of years ago, some of the creatures who died ended up in water falling to the bottom of the sea. So there you go, there's my little arrow. So dead creatures at the bottom of the sea, and at the bottom of the sea it is cold. There's very little oxygen down there, there's no light, and so things decompose very, very slowly. So what happens to them is they get buried in sand and sediment and silt. So the plant and animal remains are buried and they haven't rotted. So those chemicals inside them, like proteins and fats and carbohydrates, all of those chemicals built around carbon molecules, ends up just turning into a black sludge. So a thick, gooey, black liquid, and that is the liquid that we call crude oil. So this oil, and quite often alongside it gas, they end up trapped between below layers of rocks. And here's the green arrows representing, they want to rise because oil rises in water, but they're trapped below a rock. So what we do then is we set up an oil platform like the ones in the North Sea. We drill down through the rock, and then actually the oil wants to come out. So we put some pipes there and we collect the oil. And this is how we make a substance called, or this is how we collect crude oil. Now, look how long it's taken to make. It's taken millions of years to make, and we estimate that we've already used up most of the oil on the planet. So it's not going to last forever. The number of people who have cars and the number of products we make from oil, we are going to quickly run out of that. And by that quickly, the estimates are 50 to 100 years time, we'll have run out of all of the crude oil that was being made over millions and millions of years on the planet. So it's absolutely essential that you have the idea recorded that it takes millions of years to make crude oil. This is a process that takes an awful long time. The burying, ending up inside a rock, turning into a black sludge, takes millions of years. And so what do we get from crude oil? So here's our barrel of crude oil over this side. If we look closely at what it's made of different hydrocarbons. Hydrocarbons. And they're called hydrocarbons because they are only made out of the element hydrogen and the element carbon. Here, there are 2 carbons in a chain and then surrounded by lots of hydrogens. Here, there are 7 carbons in a chain. And the chain length can go from as simple as 1 carbon on its own to chains of a couple of 100 carbons. And so on and so on. So actually, crude oil itself, we say that crude oil is not useful. Yes, it contains this really useful chemical, and yes, it contains loads of useful chemicals, but the problem is it's all mixed in together in crude oil. It's not useful because it is a mixture of hydrocarbons. So a definition of crude oil would be a mixture of different length hydrocarbons. And the reason it's not very useful is because it is a mixture. So obviously what we need to do is separate them out. Compounds, molecules, blah. So we've just said a minute ago, they are a mixture. They're not all the same. Now, what you should remember, either from Chemistry 1, or what you should remember if you look at your periodic table that you're allowed in the chemistry exam. Sorry, the phone just rang. Here is a carbon. It has 4 electrons on its outside shell. That means it would love to make 4 bonds with other chemicals. 1, 2, 3, 4. So carbon itself wants 4 bonds. Hydrogen, on the other hand, only has 1 shell. It has 1 electron in it. What does it want to do in that first shell? It wants a maximum of 2, so it just wants to make 1 bond. So if I try to draw this one here out, I've got a carbon wanting 4 bonds. So I'm just going to put the 4 bonds on. And next to it is another carbon, and I'll put the 4 bonds on. So each carbon will always have 4 bonds coming off it. And all the rest of it is hydrogen. And each hydrogen only has the 1 bond. So that is my drawing of the bonds in this here molecule. That can be drawn like this. The other way it can be drawn is like this. C2, to say there's 2 carbons, H6. So every hydrocarbon is made out of carbons that have 4 bonds and hydrogens that want 1 bond. Every single one of these molecules on here, when you draw them out, every carbon in here has 4, every hydrogen here has 1 bond. So it's quite easy to do, and it's quite repetitive. It's not much to learn. That group of chemicals, like the one I just drew, carbon, carbon, hydrogen, hydrogen, hydrogen. We'll get bored of this in a minute. Not you, because obviously you're excited by this, watching ink appear on the screen that I am drawing live. Well, live at this moment, but not when you're watching it. That is an alkane. The meaning of the word alkane is, I'll do another one. 1, 2, 3, 4. Hydrogen, 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 to make 4 bonds around here. This one's already got 2, so I'm going to go bond and bond, bond and bond. If you go around counting that now, every carbon has 4, every hydrogen has 2. H, hydrogen, 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 hydrogen. Right, and so on. I could draw the one with 150 carbons, but that really would not add to your viewing pleasure. They're called alkanes, so this one, for example, is called ethane. They all end in the word ane. This one, well, 1 carbon is methane, 2 carbons is ethane, 3 carbons is butane, so that's 1 carbon in a chain, 2 carbons in a chain, 3 carbons in a chain is butane. No, it's not. Silly man. 3 carbons in a chain is propane, and 4 carbons in a chain over here is butane. By silly man, I meant me, not you, because I got it wrong. So, alkanes, they are made out of hydrogen and carbon. They're hydrocarbons. They have only single bonds between the carbons, and they are completely full of hydrogens. There is nowhere on here, this butane, there's nowhere on here in this molecule of butane, there's nowhere for more hydrogens to join on. So the word we use for that is, we say that this is a saturated hydrocarbon. And saturated means it's completely full of hydrogens. You can't join more on. Every single alkane has only single bonds between carbons and are fully saturated, and they are made of carbon and hydrogen only. Now, you might have spotted a pattern already. For every carbon you have, let's go to this one, there are going to be 2 hydrogens on top. So this carbon, 2 hydrogens, 1 on top, 1 on the bottom. This carbon, 1 on top, 1 on the bottom. same there, same there. But there's always one at this end and one at this end. So if we want the formula of every single alkane, here's the secret magic bit, every single alkane has this formula. C, number, so the number might be 6. H, what do I have to do with it? Well, I have to double the 6, and then I have to add the 2 on the ends. So this is called the general formula for every single alkane. You're expected to know that, know it quickly, know it off by heart, and be able to use it. So for example, if I say to you, right, the carbon has 10 carbons in a row. How many hydrogens are there? Well, what you would do is you'd go, well, I have to, 2 lots of 10 is 20, add 2, 22. There you go. So I don't have to draw it, I don't have to count them. I can quickly work out the formula of this decane. You don't need to know the name of that one. So, alkanes, just said it, they're all saturated. They are full of hydrogens. This is one way of drawing it, and it shows exactly the same information as is here, the way I've been drawing them. This then is what it might look like in a molecule, and this is what it looks like in a skeleton diagram. Now, you're expected to be able to draw and name the first 6, so down as far as here, but it's not a bad idea to know the ones below it. So what I'd like you to do is now or at some point practice drawing a few of them. You might decide, oh, here you go, hexane C6 H, oh, double it and add 2, 12, 14. So you might just practice drawing out that one, etc, etc, etc. And then over here, because this general formula 2n plus 2, you can quickly work out the formulas for these ones. Just a little bit of practice helps it stick in your head. Right, that's what you would end up with if you do that sheet. There's all your answers. You can see the pattern really clearly. Just make sure if you need to pause for a minute, do a couple of those, that's fine. And then we come to the fact that, remember what I said at the start, crude oil is not useful. So the oil is taken to somewhere called a refinery, an oil refinery, like the one in, oh, where is it? Oh, it's nearby. Oh, the name will come back to me in a minute. It's over near Calshot, Fawley Oil Refinery. And at Fawley, crude oil comes in, and what they do is they separate out all the different chains. So we need to look at how that's done. It's done in a great big piece of apparatus. This is about 50 meters high, so rather large. So they can be smaller, and it's called a fractionating column. And the process itself is called fractional distillation. Again, I'm only telling you stuff you absolutely must know. Fractional distillation is using a fractionating column, and it separates all those different chemicals that were mixed up in crude oil. Remember, you can pause whenever you want. I'm hoping you're taking notes, making mind maps, index cards, however you learn best, or even just listening this time round and then going through it in a bit more detail for the bits you need. So, here's what happens. Now, I'm going to make an awful mess on this diagram, but first of all, you heat. You do not burn, you heat the crude oil. If you burn it, it's gone. When you heat it, I'm just going to draw that as a little chain, that as a medium chain. Maybe that's 10 carbons, maybe that's 16 carbons, maybe that's 20, maybe that's 150 carbons. All these different length chains, when they're heated, are going to turn into a gas. So what happens first is we turn all of crude oil into a vapour, into a gas. We vaporise it, and it all passes into here. Right. The ones that are, the bottom here it says hot, 350 degrees. Up here it's going to be 200 degrees. Up here it's going to be 150 degrees, 100 degrees. Up here it's going to be 70 degrees, and up here 25 degrees. So it gets colder the further up the column. The bigger the chain, the higher the boiling point. What that means is, as they move up this column, what's going to happen is all of these different chains are going to, and this is what it's based on, they're going to condense. They're going to turn back into a liquid. Now, the great big long chains turn into a liquid right down here at the bottom, and they go off down this tube, and the chemical is called bitumen. You wouldn't know it as bitumen. If you were thinking on everyday words, you would call it tar. It's that black stuff on the roads that gets sticky in the summer when it's warm. Tar comes out of crude oil. It's the long chains. At the very, very top here, the only chains that make it to the very end are 1 carbon, 2 carbon, 3 carbons or 4 carbons long. They come out this pipe at the very top. And you use them for things like barbecues or caravans, so you can get propane or butane, so the 3 or 4 carbons long. You can get that in a red cylinder in Calagas, and you can get that in a blue cylinder. The next chains that are next length, these ones burn quite quickly. They're the next shortest. That's petrol. So petrol is usually between 6 carbons long all the way up to 12 carbons long. The next lot are quite good for using to make other chemicals. Then we've got this, kerosene. It's a longer chain. It doesn't burn as well as petrol. It's longer than petrol, but what it does, it burns for a longer time. So kerosene is what we call airplane fuel. And when you see airplanes landing and refueling at an airport, they're filling up with kerosene. Some people don't have petrol cars. Lots of lorries and stuff work on diesel, and diesel takes a longer time to burn, but it lasts for longer, so you don't have to fill up your car so often. So some people have diesel vans and cars because actually they don't go through the fuel so fast. Down at the bottom here we've got a fuel oil, a really slow burning oil, which would be good for like burning for ships or power stations where you don't want them to go fast. But obviously, because petrol is shorter chains and burns faster, petrol cars will be faster than diesel cars. So, what you've got to try and do, in your own words, is go from the point of view of, number one, we heat up the crude oil into a vapour. It all passes into the column. Molecules go up the column until they reach their boiling point, and then so they're going up the column here, number 2, then they condense back into a liquid. If you're a long chain, you condense near the bottom, number 4, and number 5, if you're a shorter chain, you condense near the top. So maybe pause for a minute, re-watch the last minute and a half if you need to, otherwise crack on. So, draw in the diagram, indicate the hot and cold parts. So we said the bottom was the hot and the top was the cold. Now you can match the temperature, so this is easy. 400 at the bottom, 370. It's exactly what we've just done. So, long chains. Long chains like tar, I'm just going to draw a long chain here and a short chain here. And then in the middle, a medium chain. So, long chains, higher boiling point. That means these ones at this end have a lower boiling point. These ones burn slowly. These ones at this end burn quickly. These ones, when you burn them, are really smoky. These ones at this end burn with a really clean flame. That's why diesel cars with longer chains are much smokier than petrol cars. These ones at this end are really thick. They pour really slowly. They're very viscous. And these are less viscous. So you've got to make sure that you know the properties. I would suggest you learn all of the properties for a very long chain and for a very small chain, and then you'll be able to compare any two chains. So, as the chain of hydrocarbons gets longer and longer and longer, the colour gets darker, the boiling point gets higher, and they get thicker, harder to pour, more viscous. As the chains get shorter, they're easier to burn. So we actually think that these ones at this end are the best. They're the most useful, and they're the best because they're good fuels. You can use them to burn quickly. The ones at the bottom here are less useful as fuels. Last couple of little bits. We like the short chains better. It would be lovely if we could get this great big long chain here and smash it up into smaller chains. Well, we can. That is called cracking. Cracking takes long chains and makes short chains. But we get alkanes and we also get alkenes. And the difference here with the enes is they have a double bond. So this one that's drawn here, it does have a hydrogen down here in the corner. I'll just draw it on for you. This, because I'm in the way. This one here, the carbon still has 1, 2, 3, 4 bonds, but it's not full of hydrogen. So this process of cracking, what you do is you heat it, you put it under pressure, and you may use a catalyst. And for example here, octane, which is 8 long, splits into hexane, which would be great for petrol, 6 long, and ethene, which is great for making plastics, which is 2 long. All we're doing is splitting up a long chain to 2 smaller chains, because they're more useful. Make sure you can know that cracking, if you want to crack molecules, you heat them, you can apply pressure, and you use a catalyst. You can come back to this and pause if you want. Now, we did alkanes, now alkenes. Alkenes have a carbon. Let's go for, there's the general formula. It hasn't got the +2. Let's go for an alkene. When you draw an alkene, let's draw pentene. It's got 5 carbons. 1, 2, 3, 4, 5. All I have to do then is draw one double bond. That's all they have. So the first thing is they have one double bond. So what I'm going to do is I'm just going to draw it there. There you go. There's my double bond. That means the other bonds are single. Right. Next thing I'm going to do is I'm going to put hydrogens on. This carbon at the end needs 3 hydrogens to make its 4 bonds. This carbon needs 2 hydrogens. This carbon already has 3 bonds. So what I'm going to do is just add 1 on. This carbon has 3 bonds, so I'm going to add 1 on. And this carbon at the end only has 1 bond, so I'm going to add 3 on. Now, because it's got this double bond in it here, there is room to put more hydrogens on. So when we said alkanes were saturated, that means that this one is unsaturated. It's unsaturated, it is not full of hydrogens. They contain a double bond between 2 carbons. They are unsaturated. There's one. Double bond. What I'd like you to do is pause and try and draw those 3. I'll do the middle one because I can't help myself. Carbon, carbon, carbon. 3 carbons. Double bond. Hydrogen. Is it a single bond? Hydrogen, 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 hydrogen. Every carbon there now has 4 bonds. Every hydrogen now has 1 bond. Try the other 2 yourself and then move on. There's the answer. Last thing on crude oil. When an alkene, such as ethene, because it has this double bond, it would rather have single bonds. So when you put it in bromine water, which is brown, it will join up with two bromines. So the test to find out, if I gave you a gas and I said to you, is it an alkane or is it an alkene? You would do the bromine water test. If you bubble some alkane through it, it was already saturated. So the brown water, bromine water, will start off with an alkane. It will start off brown, and at the end it will still be brown. There'll be no change. However, if I start off with an alkene that will join up with bromines, I will start off brown and I will end up clear. Not grey like the picture shows, it will end up completely clear. So what we say is the test. Any alkene, anything with double bonds, will take the colour away or decolorises bromine water. Right, that's enough on organic chemistry. Hopefully that's enough to give you the revision. You can go back to your exercise books, you can go to bite size, you can add to it, and if you're separate science, you've got a couple of other groups to do as well. Brilliant, hopefully that's been helpful.